Good afternoon, everyone. Hope you had a good weekend. Let's get started. So there's just one more slide to cover on Unit 2, and it's sort of a motivation for the next unit. So in Unit 2, we learned about multiple linear regression. In that case, we had D different features, and we came up with slope coefficients for each of those features, as well as a single intercept coefficient. And if that sounds limiting, I wanted to show you that you can actually do quite a lot with this model. So for example, if you have a single scalar variable x, and you want to construct a polynomial model from that x, what you could do is you could create multiple features by taking x to different powers. So if you want to compute a dth order polynomial model, you then get d features, and now you can apply what we learned for the multiple linear regression directly to this. Okay, so it's just a matter of pre-processing your data, and all of a sudden you can do much more than a linear model. And of course this goes beyond, so this is basically the trick here. This goes beyond just using polynomials. If you want to come up with features that are, for example, like a cosine of x to with some frequency omega j, and you can do this with different omega j's, you can get different features xj, and so on. So basically your imagination is the limit of what you can do if you just want to pre-process features and make those features maybe somehow more powerful for use in your model. Okay, are there any questions on this idea? Okay, so, but there's a catch. Once you have all this newfound freedom, the question is, well, how far do you push it? Because maybe if you, let's say you have a single variable x and you say, well, maybe there is some utility to squaring it, maybe there is some utility to cubing it, maybe there is some utility to taking it to the fourth power, then where do you stop? Do you just come up with these more and more and more complicated models? Or is there a cost to doing so? And so that's the issue that we're going to start talking about in the next unit. And concretely, in this case with the polynomials, the question would be, how do you choose that polynomial order d? Because you can go as high as you want. So how many of you guys think that higher d is going to be better? Okay. And how many think that higher d is not necessarily better? Okay, right. So of course we have to define what we mean by better, but in most cases, yes, higher d is not going to be better for the practical problem we want to solve, which is getting our model to work well on some data that's independent of the one we trained it on. In that case, higher d is definitely not better. So let's move on to the next unit then, which is all about model order selection, basically choosing that d in a polynomial model, or more generally, if you have some choice of a complicated model or a simple model, how do you choose the complexity of the model? And we're going to get into a little bit of random variables and statistics and stuff here, and we'll talk about the bias variance trade-off, which is a very fundamental idea in machine learning that tells us, it kind of encapsulates the problem with choosing a model that's either too simple or too complex. Okay, so let's sort of start where we had left off with polynomial regression. So in this case, as in the last slide of that last unit, we're saying we have a single scalar variable x, and we're going to come up with a model that says the target y is approximately equal to beta 0 plus beta 1x plus beta 2x squared, and so on, higher and higher powers until you get to beta d x to the power d. And for some reason, we decide to stop there. So the question is, where do we stop? What d or what polynomial degree do we choose? And because usually in machine learning, we are not in a situation where an expert tells us what to choose, because machine learning is all about learning from the data itself. we would like to see if we can learn D from the data itself, rather than having someone tell us what the right D is. Okay, so this is an example of what we call model order selection. Okay, any questions so far? Okay, so so we're not going to have a real world data set. Oh, question?
Can D be not whole numbers?
Not in the case of polynomial model. Do you have any other? I mean, I guess yes. We will see actually. More generally, we will see in the next unit, Unit 4, actually a case where the complexity is controlled by something that's not an integer. It's like a real number. Another question?
Yeah, while learning the model, if we figure it out, the polynomial is like, let's say 4, and the regression is like nearly to 1, like 0.8 or 0.9.
And what is 0.8 or 0.9?
How do we get to know which order polynomial fits the best?
Well, that's the whole goal of this unit. Yeah, so it's a great question, but that's what I hope to teach you in this unit, is that. Okay, so so like I said, we're not going to use a real-world data set. We're going to use synthetic data. Synthetic data has some advantages, especially when you're trying things out or teaching things. So in particular, like we know the truth, right? We know the ground truth. So if you know the truth and you have a hypothesized approach, you can test it and you can get a very clear judgment of how good or bad that approach is. When you work with real data, you don't always know the truth. And so it's hard to say whether a given model is better or worse than another one. Okay, so so in particular, we're going to generate this synthetic data. We're going to choose our features, xi. So of course we have a single scalar feature, but we're going to build a data set synthetically. So we're going to choose many samples of that single feature. We're going to choose 40 of them or generate 40 of them. They're going to be uniformly distributed in the interval between -1 and 1. Now for the target values, we are going to generate them using a particular model where we have some function of those xi's, a deterministic function, plus a random noise that we're going to call epsilon I. Okay, so this deterministic function, we can think of that as sort of like the noiseless targets. And in this case, that is going to be a polynomial. So this is our function fx, and it's going to be a third order polynomial. That's the true one. Of course, we won't always assume we know that. We're going to try to learn that from the data itself. But there is a true value for D, it's 3, and there's true values for those beta coefficients. They're going to be things that we randomly generate, but once we generate them, we're going to take them to be the truth. We're going to construct our data from those values. For the noise, we are going to use zero mean Gaussian noise. And so a notation that will start to show up more commonly is this. So this tilde means distributed as. So these epsilon i's are distributed as, and then the script n is, you can say it's normal or Gaussian. That's what the n is. This 0 is the mean, so this is zero mean, and sigma squared is the variance. Okay, so this is just a shorthand notation to say we're going to generate samples of noise. Each one is going to be an independently generated sample from a Gaussian or normal distribution with zero mean and sigma squared variance. And here's the code. So we're going to help us do this, we're going to use the NumPy polynomial library. It has a lot of interesting, convenient routines. So, oh, actually, I said wrong. The beta coefficients are not random. They're just set at these numbers. So 1.5.2. The standard deviation we set, which is sigma, we set that as 0.4. And we generate here 100 samples. Actually, I'm not sure why this says 40. It should say 100. 100 samples, and you can see Here is where we generate the data. We're using this NumPy random library, which has a uniform distribution. We tell it generate 100 samples from -1 to 1. And those are the values of the dots along the horizontal axis. So you can see there's 100 samples. Now, in terms of the vertical axis, first we create this sort of noiseless target curve. We do that using the polyval command that evaluates the polynomial. It evaluates with the data in this vector using the coefficients in this beta vector. So that gives us the noiseless targets. And then here is where we add onto the noiseless targets our random normal distributed noise. And that is how we go from this red curve to the dots. Okay, so the dots, the blue dots, are what we finally get as our data set. And you can see there's quite a bit of noise in there relative to, that red curve. Okay, any questions so far? Okay, so let's first think about what happens if a Gini tells us the true model order, and we know that, and we do the fit. So as we can see from this plot down here, the true curve is the red one. That's from the previous slide. But now we're superimposing this green curve, which is for the beta coefficients that we fit using least squares, using exactly the same techniques we learned about in the last unit. When we use those coefficients and generate a new curve, it's that green one, and it's almost perfect fit to the truth. It's not perfect, but it's very close. Despite all the noise, least squares works quite well, at least with 100 samples and so on. Okay, so now how did we do this? Well, we could have used the linear regression methodology from scikit-learn that we learned about in the last unit. If we wanted to do that, we would have had to manually construct our features. Or actually, scikit-learn has also some routines to go and do this polynomial expansion. But we are going to just keep using the NumPy polynomial package, which is convenient for generating these curves, but also it can do the least squares fitting as well. So that's in this line here. This polyfit does least squares fitting. You give it the x data, the y data, and the model order D of the polynomial, and it produces the coefficients. Okay, so that is essentially the approach we're going to use in this demo is use the NumPy polynomial. Okay, any questions so far? Okay, so the interesting thing now is, what if we don't know the true model order? So let's first consider what happens if we underestimate it with almost the simplest thing that we could do, which would be just simple linear regression. So as we know, when you do simple linear regression, you can fit a line to the data. You can adjust the intercept and the slope, but that's it. And so when you do that for this particular data set, you get this green line, which you can see is it's not a terrible fit, but certainly it's not as good as the polynomial one. Okay. And when you use a model that is too simple compared to the truth, call that underfitting. On the other hand, you can go the other direction. You can use a model that's too complex relative to the truth, in which case you call it overfitting. And here's an example. If we use a 15-order polynomial model, this is what we get. So it's, at least in this region, it's not terrible, but then some crazy things start to happen when you go outside this region. So, so that's an example of overfitting. Just to provide another illustration, that's just something someone drew. Really, it's not from true data. Maybe if your data looks like this, that would be an example of underfitting. This is an example of a good fit, and this would be an example of overfitting, where the key point here is that in some cases, when your model is sophisticated enough, it can actually fit whatever data you give it perfectly. So it goes through all those data points. So from perspective of fitting the data, it's perfect, but that's not going to be a great thing when you actually try to apply this model, because when you apply this model, maybe somebody gives you a new sample that, you know, had maybe the new sample was here, and all of a sudden now the model is not agreeing with this new sample. Okay, so the question then that we're still trying to answer is there a way to estimate the true D from the data? That's our whole goal right now. Question?
So when overfitting, when there are new data samples outside the range, it's going to be crazy. But if we know that the range will definitely be between some certain numbers, will it be possible that trying to make it overfitting will actually result to a better performance?
From the sort of classical definitions that we're going to be focusing on here, overfitting is generally a bad thing. There are certain examples that have recently been uncovered in statistics and machine learning with very high dimensional models where overfitting is actually benign, but those are a little bit outside of the scope of what we're going to try to learn right now. But I don't know if you're thinking about that in your question, but there are some examples where you can overfit with the right kind of model and it will handle it in a very nice way. But in general, overfitting for us is going to be a bad thing, and that you can do better if you use the true model order rather than a more complex one. Okay. All right. Any other questions? Okay, great. So, so now let's start with maybe kind of a naive idea, but based on what we have talked about so far in the course, maybe this is really the only thing that we're capable of doing. So as an approach to try to figure out the correct D, we might do the following. You hypothesize D equals 1. You fit a least squares model with D equals 1, and you measure the RSS you get on the test samples, or sorry, on the training data set. Now you repeat that for D equals 2. Fit a least squares model for D equals 2, compute the RSS on your training data set, and measure that. And then you do this for higher and higher D until you run out of patience. And then you look at what you have. So that's sort of what I'm describing here. Right? For each hypothesized model order D, compute the least squares coefficients. There's going to be D plus 1 of them. Compute what I'm calling here the normalized RSS. So in this unit, instead of talking about just plain RSS, we're going to normalize it by dividing it by 1 over n to control for the size of the data set. And that's going to be more convenient for us in this unit. So, so that's the idea. Just try different D, compute the normalized RSS, and then choose the one. This is kind of the key point here. Choose the D to minimize the normalized training RSS. So what do you think? Is this going to work? Okay. It's kind of a giveaway because it's discussed on the slide here, but this is an example of what you would find if you do that. So here's the model order. This is the hypothesized D. And you can see that when D is too small, like 1, of course, the RSS is super high because it's a really way too simple model. Even D equals 2 is too simple. Once you get to the true model order, D equals 3, all of a sudden you get a big decrease. But then, if you try higher and higher model orders, you get lower and lower training RSS. So this is training RSS. So that would, if you use this approach, you will basically always choose the largest D that you hypothesize. And that will lead to overfitting. So this is not going to be a successful technique. So the question is, why does this happen? Does anybody have any ideas? Yeah.
It starts to trace each data set or data point.
Yeah, that's So the answer was you start to fit the data rather than like the underlying model, I think, right? And that is exactly a really nice interpretation of overfitting. I think I have that written on the next slide. Let me try to explain overfitting from a slightly more mathematical perspective, or not overfitting so much, but like why this training RSS is not the right metric to use. So if we try to, if we think about this approach where we try more and more complex beta vectors, in other words, beta vectors with more and more non-zero coefficients, we can just sort of write them as sort of as a set of vectors. So for example, maybe if I start with model order d equals 1, my beta vector has a beta 0 that I can adjust. It has a beta 1 that I can adjust. But then essentially I'm saying I'm not allowing any of the other higher order coefficients to be non-zero, right? So in some sense, I'm forcing them to be 0. So I can just write those as zeros. On the other hand, when I choose d equals 2, my beta vector has an adjustable beta 0, an adjustable beta 1, an adjustable beta 2. But then after that, it has 0 coefficients. I'm forcing them to be 0. And so on. When the beta vector is, when d equals 3, the beta vector has beta 0, beta 1, beta 2, beta 3, but then it has zeros after that. Okay, so when you step back and you look at these different beta vectors, you can see that each one is a more capable version of the last one, because like in this one, I'm allowing beta 2 to be non-zero, where here I'm just forcing it to be 0. So this model can do more because it has more degrees of freedom. Certainly can do no worse, because I could always set this to 0, and then it would be this model. But here I'm allowing it to have more freedom there. And then with the next one, I'm allowing it to have more freedom here. And if I take my goal as minimizing training RSS, and I'm designing these to minimize training RSS, then I will only do better and better with my goal as my model gets more and more capable. So that's sort of an explanation for what happens. As each model is more capable, and as a model becomes more capable, the ability to minimize training RSS improves, and so the largest D will always yield the smallest training RSS. And in fact, if you take this to an extreme, let's say you have a data set of n samples. If you select D greater or equal to n minus 1, and if your samples are random enough so that this matrix A has a full column rank, that's what you would say in linear algebra, then it will always be possible to force your RSS all the way to 0. And when you do that, your whatever, in this case, your polynomial curve perfectly passes through all the data points. And you are, exactly as what was suggested, you are basically fitting the noise. I mean, you're fitting not only the true model, but you're fitting the noise on top of the true model. And that's a really nice way to think about what happens when you overfit. Is you're fitting stuff you don't want to fit. You're fitting noise that is not going to be there in the practical real-world problems when someone gives you new data. It's not going to be the same noise anymore. It's going to be another random noise, and so when you fit to this first noise realization, that's not going to be what you want to do. Okay, so that's some intuition on overfitting. Any questions on overfitting? Yeah.
Can overfitting be solved with just increasing the data pool? So it looks like if there isn't a bunch of points, you can just perfectly get the lines. So if you got a bunch of data, will that solve overfitting?
You'll still have everything on this slide here, except that this goal will be harder to achieve. But like everything here will still hold. So like if you say my goal is to minimize training RSS, no matter how big your data set is, as your model order increases, you'll just be able to do that better and better and better. So essentially that will tell you always use the largest model. But then in practice, you will still find that no, that is not going to be the best model when you apply it to test data, what we call test data, which is different from the training data. So yeah, so basically things change, but the problem doesn't go away. Okay, all right, any other questions? Okay, so now let's talk about strategies to circumvent this problem, basically, we know that just choosing D to minimize training RSS is not going to work. So can we do something different? So essentially, the answer is yes, and it's called cross-validation. So cross-validation is sort of a term that encapsulates a lot of different schemes. So let's start with the general idea, which is to evaluate your performance on test data that is independent of the training data. Okay, so the training data is still being used to train your model. It's being used, for example, to adjust those beta coefficients. But then, to evaluate which model order you want to use, D, you don't want to use training RSS, you want to use test data that is somehow independent of the training. Okay, so there's a difference here between what we mean by evaluation and what we mean by training. Sometimes people call this evaluation, they'll call it validation. It's another commonly used term. Okay, so here's the simplest way to do that. You take the total data you have been given, and you split it into two subsets, also known as two folds. You treat one of those folds as the training data from which you determine your beta coefficients, and the other fold you use to evaluate the betas that you trained. For example, you can compute normalized RSS on that, and that is going to work a lot better because, from one perspective, you avoid overfitting because it's impossible to fit to test noise that is unseen during training, right? When you trained, when you came up with your beta coefficients, you did not use the test data, so it was impossible to fit to the noise in that data. So that's how we can get around this issue. Okay, so maybe we'll use ntrain for the number of training samples, ntest for the number of test samples. And this is just a partition. It's just a simple splitting in two. Now, you want to be a bit careful when you do this. Typically, you want to shuffle your data first because it's not unusual to find a data set where the targets are maybe organized. They're somehow ordered. So maybe, for example, someone ordered the targets from small to big. And if you just split the data set into, let's say, the first half and the second half, then you'll find that in the first half, the targets are always small in the training set. And in the second part of the test set, targets are always big. And you're going to have terrible test performance because the training and test sets are very different. So you want them to be as similar as possible. So one way to do that is you just randomly shuffle all the training indices, shuffle up that data, and then statistically, what you find in those two folds will be very similar.
Is it ever better to make the training set bigger than the testing set?
Yes, that's a great question. So here we haven't really said how to choose and test and train. So essentially, that is one of the that's one of the troubles with this simple approach, is that you have to make a difficult choice. So sort of intuitively, the more training data you have, the better fit you should get, right? And we'll actually see this more concretely in Unit 4, but I think it's intuitive that we want more training data, right? At the same time, if our test data is too small, the evaluation will be random or noisy or somehow it won't be right either, right? So we also want our test data to be large. And so the question is then, well, how do you deal with this if you have zero-sum game? You either use a sample for training or test. What's most commonly done, I would say, is an 80-20 split, 80% training, 20% test, but there's really no like magic ratio there. It's just people try different things depending somewhat on how many samples you have. Okay, great question though. So basically here's, as an algorithm, this is how you would write the 3 steps of this algorithm. You do this partition, and maybe I'll write here shuffle. Then, for each hypothesized model order D, we have a for loop. You compute the least squares coefficients from the training data, so there will be D plus 1 of these. You then use them to predict your test targets. And now that you have predictions of the test targets, you can compare them to the true test targets. And here we're computing the normalized RSS. But now since we're using the test data, we're going to call this normalized RSS test. So this is different than previously we called it train, normalized RSS train.
So, if the RSS can be like minimum for the overfit data also, right? It is not necessary that a good fit model can give you the minimum RSS.
That's right. This approach is certainly not perfect.
So then are we going to, in the training setup, training data, we split into different subsets and train it and pick a best out of it? Like,
We'll talk about that next. Yeah. This is just the simplest approach. And this approach, because of its simplicity and efficiency, actually is used it's the main approach people use for deep learning. So, but if you have smaller, the data sets are gigantic and the models are gigantic and you just don't have time to do something, let's say, more fancy. But if you have a smaller data set and training doesn't take very long, we can do better, and we'll talk about that on the next page. Okay, so let me just show you, though, what happens with our polynomial experiment. So the blue curve is what we saw on the last page, and you see that one just gets sort of, the training RSS gets better and better as the model order increases. But now the test RSS, you can see it's lowest in this area, which is close to the true model order. The true one was here. It's not perfect, though. In this particular case, this value of test RSS was slightly lower than this, and so actually this approach chose model order 4. Probably is not a terrible choice, but it's not correct, and so we'll see if we can improve on this in future slides. But the overall idea here is sort of what's important: evaluate performance and test data that's independent of the trained data. Yes?
Is there some approach to take into account both the NRSS of test and training, minimizing both?
I haven't heard of doing that. I think it's that the training data will kind of corrupt the test data. So usually you really want to keep them separate.
Okay, I think I mean like the test data will have like an NRSS value and it will still minimize that defined the order. Is there an approach to looking at both the NRSS and training and?
Yeah, no. So what I was trying to say is, like, when you do the validation, you want to do everything you can to make sure none of your training information snuck in. So you don't want to use like the normalized RSS from training at all. You just want to, and there's much more sneaky ways that information can leak from training to test. And so usually you want to just try to stop that. Okay. So here are some more sophisticated ways. Like we just said, the simple split faced a difficult trade-off between how much data is used for training and test. So there's some ways to get around that if you allow more computation. So a very well-known approach is called k-fold cross-validation. And so here's how it goes. You take your whole training data, what you're working with, and you partition it into k different folds, k being some number that is at least 2, more typically 5 or 10. In this picture on the right, it's going to be 10 folds. So what you then do is you use one of the folds of the k as the test fold, use all the rest as training. So then you fit your model based on this, you test based on this fold, and you save that value. Now you repeat the process where now you use the second to last fold as a test and use everything else as training. And now you'll get you get different beta parameters, you'll get a different test RSS, you store that. So here's the values we're storing. You repeat this procedure k times because you have k possibilities of what that test fold can be. Okay. Once you're done, you will have k different normalized RSSs, and you can average them to get an overall value for what you think the quote-unquote test RSS is. I'll try to call it the cross-validation RSS to be a little more clear. Okay, so this is k-fold cross-validation. What's unfortunate about this is you have to do the parameter fitting k different times, and sometimes that parameter fitting can take some time, some computation. So you have to wait k times as long to get your answer. That's the main downside. Like I said, typically use 5 or 10 for k. There is sort of an extreme case of this, which is leave one out cross-validation, and that's exactly the same idea, but that's where for k you use n, the number of samples in the data. So that means that the test fold always has one sample. And you have to now, if you have n data points, you have to fit n different models. So this, if n is large, this can take quite a long time. But in some sense, that's maybe the most accurate version of this, where you get to use as much training data as possible for every fit. But it just takes a long time. Okay, so all right, so those are the main approaches to cross-validation. There's a simple test train split, and there's the k-fold approaches. Any questions? Yes.
So after the k-fold cross-validation, we should have for example, we should have 10 different data metrics. So what is our final data?
Oh yeah, sorry, great question. So what we do in the end, once we have determined our model, so let's say we use all this information and somehow we find that we want to use d equals 3. Now we go back to our training data set and we use the whole entire data set to fit the betas with the model. So this is sort of a temporary thing we do just for the purpose of model order selection, and then we go back and we use all the data we have for training. Yeah, great question.
Is the second one always gonna be better than the first one because the validation set of the second approach is always gonna be 1, so is there gonna be some randomness?
Well, it's gonna be, the validation set is small, but you have many validation. So so I think you would find that there's more randomness as k is smaller. So yeah, as it's faster and smaller, like k equals 2, k equals 2 is very similar to the test train split, except the only difference is you use one for train, one for test, and then you swap them. And that doesn't take much time, but the numbers you get are still quite random. So as k increases, you get less and less randomness. Yeah. Okay. Great questions. Any other questions? Okay. So let's talk a little bit about how we implement this in scikit-learn. And there's sort of a manual way to implement it, and I think that's what we want to understand right now. There are more automated ways of doing it, which we will learn later, but I think it's helpful to understand the random approach first. So essentially, we do this with 2 nested for loops. So in the outer loop, we are going to index over or loop over the test fold k. So in other words, in the outer loop, we're doing this, and then this, and then this, and so on. In the inner loop, we're going to loop over our model orders. So we're going to have to decide which ones we want to test. For example, in this case, maybe we want to test model orders between 1 and some capital D, which we have to choose. And we'll just loop over those. So that means that when we're in that innermost loop, for each value of model order D and test fold K, I can compute a normalized RSS for that particular pair D and K. Once I've gone through all those loops, I can then average across the folds, average across the test folds, and now I'm going to get what I'm going to call an NRSS bar that's a function of D. So this is like a sample mean across the folds, but I'm going to have one value for each D. So then now I can plot a curve like these curves versus D. And from that curve, I would just look for the minimum point. That's the simplest approach here. We would just choose the D, giving the smallest k-fold normalized RSS. Okay, so that's the overall approach just from perspective of words. If that's clear, we can dive into the code. Everybody good? Okay, so one of the most complicated things, if you would actually just try to program this from scratch, one of the most complicated things you would find to do is coming up with all the different index sets into your training data to make these different folds. So if you think about it, like each one of these is a set of indices through your data. And we've probably shuffled before we've done this. So this is going to be some random looking set of indices. This is another random looking set, and so on. So all that stuff is taken care of by this k-fold object here. So this is in the scikit-learn model selection k-fold. You set up this object, you tell it how many splits you want to use, and you tell it whether you want to shuffle or not. Almost always want to shuffle. And it builds this k-fold object, and this inside it will then have those splits of indices. It will know exactly the indices to use indices to use for each of the folds of the k of them. Now that we have those, things are pretty straightforward. So here we're setting up the different D's we want to test. So here we're going to start at 0 and go up to 9. And we're going to initialize a normalized RSS cross-val. So here's an interesting thing. If you're new to Python, there's sort of a nice way to do for loops in Python that's a little bit more sophisticated than in MATLAB. So if you look at this for loop, there's actually two different indices here. An index which is iSplit, and one which is, here we're calling IND. This first one is always going to start at 0 and just count 0, 1, 2, up to however many things are in this piece of data here. So this piece of data, this is just something that is what they call iterable. It's something that you can count. So it could be like a list in Python. It could be a NumPy array. It could be anything that has a very clear, like this is the first piece, the second piece, and so on. So what will happen in this command, this quantity will go through and it will take out the first element in this, I'll call it a list. Then the next time you go through the loop, this will take out the second element in this, and so on. So we're kind of counting through both a standard counter as well as the elements of this in this command. Okay, is that clear? So you'll see this a lot in the code because it's a very convenient thing to do. Okay, so this is what happens in the outer loop. So you're going to extract this index thing from this list, and okay, so what it's doing is you're telling this k-fold object, you're giving it the X data, the feature data, which is informing it how many samples you have. That's really what it's using from that. So now that it knows how many samples it has, it can actually do the split. And in this index object, it contains both the training and test indices for that iteration of the outer loop. So in other words, it tells you the first time you're going through, it will give you these are the training indices, these are the test. The next time it goes through, it will say, these are the training indices, these are the test, and so on. From those, you just unpack them this way. It's Hoople. There's basically two pieces. You can unpack them like that. And once you know those indices, it's very easy to take your overall data and partition it into training and test. You can do that for your targets, your features as well as your targets. Okay, so that's the outer loop. Any questions on that? Okay, so in the inner loop, again, you have one of these things where now you're going to enumerate, you're going to have a counter it, but you're also going to enumerate over the different D's in your D test vector. We could have started at 5 and gone to 7, and then this would have been like 5, 6, 7. And here's where we do our least squares fitting. And here's where we measure the normalized RSS on the test fold. So this is sort of a manual way to do it, but it shows you what's going on in this process. Okay, any questions? Everybody good? Okay, great. All right, so now we can actually improve things a bit if we realize that when we do k-fold cross-validation, what is reported to us by this k-fold process is not going to be perfect. In fact, one way to see that is, there's random numbers associated here with how you shuffled your data. So if you run your code once, you're going to get one particular shuffling, and you will find one particular set of values here, one particular average. If you run your code again, you'll have different random numbers, different shuffling. You'll get different numbers for all this. So every time it will be a little different. Right? So it's just an indication that it's never correct. It's always a little different. There's always a little bit of randomness or noise in these estimates of perhaps there's a true underlying normalized RSS, something that we wish we could get at, but we're just given finite data and we're just getting different estimates of it every time. So the question then is, well, how imperfect is this? Can I quantify it? Can I put error bars around it? Can I put confidence intervals around it? And the answer is yes. And the most common way that people do this is through something called standard error. And you can use this standard error approach on any kind of estimate that you create with an average. So for example, you're doing some scientific experiment. Maybe you're repeating the same thing 100 times, and every time you write down a number, and then you average it to try to see what's happening on average, right? That's a very common thing you would do. Well, if you want to get confidence bounds on that, you would use standard error. So I just want to emphasize this thing I'm describing here. I'm going to describe it in the context of normalized RSS for cross-validation, but actually it's a much more general thing you can apply anytime you have an average-based estimate. Okay, so this is how you do it. You compute this, so the definition of the standard error goes like this. So we want, it's a fraction, so in the numerator, we're going to have the standard deviation of this quantity, let's say the true quantity, normalized RSSD, divided by the square root of k, which is the number of samples we used in the average. So this is sort of intuitive, right? Like if you do more and more trials, if you average more and more trials, you expect the average to get more and more accurate, right? And you can see exactly that here because k gets larger and so your standard error gets smaller. Okay. We will learn more about where this comes from in a few lectures. So I'm just going to say this is what it is and not explain it other than giving you some intuitions. In the numerator, we have the standard deviation of the data. So right now, we've seen standard deviation from the perspective of sample standard deviation. So if somebody gives me a list of numbers and asks what's the standard deviation, we know how to do that. We subtract the sample mean. We average the squared value of the result. That gives us the sample sample variance. And then we would usually take the square root of that to get the sample standard deviation. Right? That's how we described it back in Unit 1. So here is a slight refinement of what we're going to do. So this is the equation that I just described in words for the sample standard deviation. Here's the sample mean, we subtract it. Here is squaring. Here's an average, but notice that we have, instead of using 1 over k, now we're using 1 over k minus 1. That's different from what we did in Unit 1. So this is what's known as the unbiased estimate of the variance. And even this, I'm going to hold off on describing what I mean by unbiased for a couple lectures, but we'll get into that. And generally speaking, this is going to give you a slightly more accurate answer, especially when k is small. You can actually see that the difference between 1 over k and 1 over k minus 1 is very slight when k is large, but it could be quite significant when k is small, right? Like when k is 2, it's pretty big difference, right? It's 1 versus 1/2. Okay, so this is something, because with cross-validation, if k is 5 or 10, that's a pretty small number, relatively speaking, so that's where you'd want to use this. And what you get now are essentially, you could think of them as error bars on how much you should trust this quantity that you computed with this average. So here's, in our polynomial experiment, here's our normalized RSS bar. That's the same thing, similar to what we've plotted before. Ideally, this would go to 0 at the true model order of 3. You can see it's not clear whether it goes to, it gets minimized. It's not clear whether it's minimum value there or somewhere else, but it's pretty good there. But now we're using these error bars to show the standard error. And you can see that the standard error actually fluctuates depending on which value we're talking about. For some, it's large. For some, it's smaller. But the basic meaning is that even though, let's say for d equals 1, the normalized RSS bar is this particular number, you shouldn't think of it as perfect. You should think of it as, well, it probably has some error in it, and the error, these are those error bars give you like a reasonable range of what it could actually be. Okay, so that's what this standard error is, and that's we'll see how to use it in just a second to improve our estimate, but this is useful in general whenever you compute an average from a finite number, k of samples, and you wonder, how good is my average? Standard error tells you essentially how much you should trust it. So it's the main way people plot error bars in papers, in scientific papers. Okay, any questions about standard error? Okay, so here's the code. Oops. So this is how we compute our mean normalized RSS. You can see we're just using NumPy mean, and this is a matrix. It has D going down the rows and K going across the columns. So we have to tell it which way to take the mean over. We're taking the mean over the columns. So we say axis is 1. If we wanted to mean over the rows, we would say axis equals 0. Okay. The way we compute normalized RSS standard error is when we call this NumPy standard deviation command, we can essentially tell it what value to use here. So, and we do this using the DDOF parameter. So DDOF equals 1 means put a 1 there. So if you want the version from unit 1, you could put in DDOF equals 0, and then it would be 1 over k. If for some reason you wanted it to be 1 over k minus 2, you could put in DDOF equals 2. But that's how we're specifying that we want this so-called unbiased estimate. Okay. And everything else is pretty standard. We're using the error bar command in Matplotlib. Okay, so that's how we can get confidence bounds on the values returned to us through cross-validation.
So what's the DOF works? So what does it do?
What is it? Can you say it again?
And the number 1. So what's it for?
By setting this number equal to 1, we say that we want to do k minus 1
So
in
what's
the...
difference between like 0, 1, 2, or 3?
Okay, if we would do it 1 over k, that would give us what's known as the biased estimate of variance, and this gives us an unbiased estimate. And I'm going to have to hold off with the definition of bias just for 1 or 2 lectures, but I'll describe in gory detail what we mean by bias.
So when it's 2, it's, what's 4?
I don't offhand know when you would use 2, but I think it's sort of a standard framework they probably use in various other commands. And so like, it's just like, I think there's probably other places where you would want to use a 2 and this is what they do.
Got it.
Yeah. Yeah, so, yeah, basically, loosely speaking, unbiased means that the errors in the variance are going to be on average 0 compared to the true statistical variance. So sometimes they'll be larger, sometimes they'll be smaller, but on average, there won't be an error. The biased estimate will always be a little smaller, well, will tend to be a little smaller than the truth. So, but we'll see what we mean exactly by that in a couple lectures. Okay, so the very last thing I want to talk about is a particular trick that you can use that you can actually get a better estimate, known as the one standard error rule. And this is a rule you can use in many ways. We're going to use it for RSS, but the rule goes like this. Use the simplest model that gives performance within one standard error of the best model. Okay, so maybe you've heard of Occam's razor, the idea that the simplest explanation that's correct is the best. That's essentially what we're saying. If there's a bunch of different model orders that all give you reasonably good performance, like all these here, choose the simplest of them that's still good enough. Okay, so this is how you do it in detail. The first step then is you find the best model. You find the D that minimizes this. And in this case, the best model turns out to be the true one. It's not always that way, but in this case, it was the true one. And then you set a target RSS, which is going to be the performance at the best model plus the standard error also at the best model. This target is this yellow or orange line that's sitting right on top of the error bar of the best model. So here is your D-min. So this is your RSS target. This is like the value of RSS that's good enough, essentially. Actually normalize RSS target. And finally, find the smallest D such that the normalized RSS at that D is less than or equal to this target. And that's because with polynomial models, smaller D means simpler. Okay. If you have some other model where a larger value means simpler, then you would find the largest of that value. We'll see an example of that in the next unit. So this is just use the simplest model. Okay, so there's actually, I updated these notes, but it looks like so yeah. In the old version of the demo, which had a different seed, basically what was happening is the minimum was 7, but the one standard error rule was selecting the correct one. In this particular, when I ran it this time, the D-min was actually at the correct value, and then the one standard error rule is just keeping it there. Okay. But I think, but like for example over here, in this case, we had D equals 4 selected. If we computed error bars here, then we would get something like this, and the simplest one that sits under that target would be the true one. So that's the one standard error rule, and that's often a way to prevent the not uncommon case that the minimum one is a little bit more complex than what you need. Okay, so I think that's enough for today. See you guys on Friday.